Welcome back. This video is going to be the last in my series of videos on tree-based machine learning methods. I'd like to give you a taste, just an introduction to one of the most important tree-based models. And so this is called a boosted tree. And let me say that this is one of the top tier classifiers among all machine learning methods. So there have been a lot of these surveys that apply, all the main machine learning methods to dozens or hundreds of different benchmark problems. And boosted trees will be one of the better ones, up there with support vector machines, random forests, and neural networks. So this is definitely one that you want to know something about. So boosted trees are in some ways similar to random forests, but they do some things differently, and it's kind of important to understand the different philosophy that's followed by these boosted trees. So I'm gonna focus on only boosted regression trees in this lecture, and that'll give you a sense for how stuff works. You can go read about boosted classification trees and trees for count data and other methods from the Hasty-Tibshirani and Friedman Elements of Statistical Learning book. That gives a bit more comprehensive treatment of this model. So the basic idea here is that we want to fit a series. So series means you're going to add up a bunch of trees again. So kind of like random forests, where we add up a bunch of trees and divide by the total number of trees. But instead of building very complicated trees, so remember random forests will build trees that maybe even overfit the data. We're going to build very simple trees. So there's a couple terms that you should know. One is that of a stump. So a stump is the simplest of all possible models. So let me just bring up my document camera here, and I'm going to illustrate what a stump looks like. So we got to get my spotlight right. So a stump would be a tree that just has one split. So that would be a tree that is a stump. So x greater than 5, x less than or equal to 5 would be a stump. I guess I need to make it a little bit bigger too. So that would be a stump. I like to call trees with maybe one or two more splits a shrub. So instead of having a full-blown tree, this is like a garden shrub. And so if I were to add an additional split here, maybe we have, so that was x1 greater than 5, maybe we have x6 greater than 10 versus x6 less than or equal to 10. That has two splits. So this is an extremely simple tree. So that's idea number one is we're going to fit a bunch of very, very simple trees, and then we're going to add them up. Now, the next big idea that is very different from normal, random forests is that each subsequent tree that we build is going to be built to predict the residuals from the previous trees. Okay, so in other words, we're going to devote our effort to explain what has not been explained yet. So the residuals. So what is a residual? Residual is just y minus y hat, right? That's our residual. That's the residual. That's what's left over. We're going to focus our effort on predicting what's what hasn't been explained yet. So if we've already explained it, then don't bother explaining it again. The third big idea with these boosted trees is that we want to learn extremely slowly. We're going to slow the learning rate down to a crawl so that we don't learn too quickly, in which case we're going to be overfitting. So the way we're going to do this, carrying on with our tree metaphor, is we're only going to use a sliver from the current tree and not use the current, stump. We're going to use a sliver from the stump. So let me give us a kind of a more precise statement of the algorithm. So in the beginning, what we're going to do is form an estimator that is just equal to 0 everywhere. Now, if you think about it, if I take the residuals from this model, if I take y minus y hat, well, what's y minus 0? Well, y minus 0 is just y. So my estimated residuals at the beginning of my algorithm equal to y's. And so another way to think about this is, at the beginning of the algorithm, everything in y has yet to be explained. All right, what do we do next? Well, we're going to have a very long loop. Okay, so b is going to go from 1 to typically a very large number. So it could be in the thousands, perhaps even more. And so during each iteration of this loop, we're going to do the following. So I'm going to go fit a tree, really a stump or what I call a shrub, with D splits. So a stump would have exactly one split. A shrub is a little bit bigger than a stump, and maybe it has D equal to 2 or 3 splits. But we're not going to have big trees here. These are going to be very small trees. And what we're going to do is predict the current set of residuals. So the first time through, these residuals equal y. And so I'm going to say, if I could introduce extremely simple tree with 1 split or 2 splits to predict y, what would that split be? The next thing we're going to do is update our estimate. So lambda is going to be what's called the learning rate. And you can think about, I'm going to take a lambda slice of the current tree or stump that I've estimated. Okay, so if I have some split that I introduced, well, I'm not going to take all of it. I'm going to take just a small fraction of it. Typically, values for lambda are like 1%. So this is exactly how I implement this this philosophy of learning very slowly. Okay, having updated my prediction, I'm now going to update my residuals. So we've done a little bit more explaining, so we don't want to explain that again. Therefore, the new residuals will just be the old residuals minus lambda times this updated tree. So we've learned very slowly with a series of extremely simple trees. And if you think about what's happened, the final model then is just going to be a sum of lambda times all my trees. So because I've slowed down the learning so much, and I've not allowed myself to have very complicated trees, typically this b is going to have to be quite large. All right, so that's the basic idea. But I want to point out one very important implication of this specification of the final model. And that is, if I have one split, okay, so remember what one split looks like. One split looks like this. I have x1 less than 5, or x1 greater than 5, I guess is what I said. X1 less than or equal to 5. That thing only involves one variable. There is no interaction there. I'm incapable of capturing an interaction. So if I have 1,000 of these simple one variable splits and I add them up, I end up with an additive model. So the implication here is, if you suspect that there are interactions in your data, you need to set the number of splits to something bigger than 1. So let me just pause and point out the tuning parameters. So all of our machine learning methods have various hyperparameters that have to be tuned. So nearest neighbors, it was the number of nearest neighbors. Bin smoothers, it was the number of bins. For ridge regression, it was the penalty term. In this case, we actually have 3 hyperparameters that we're going to have to tune. So number 1 is how many trees do you want to fit? So that's B. And we're going to see how we tune that in a minute. Another thing that you may want to play with is the learning rate. In R, the learning rate lambda is known as shrinkage. So typical values are somewhere between 0.001 and 0.01. So as a general rule of thumb, the smaller you pick lambda, the more trees you're going to need. The more aggressive you are in your learning rate, the fewer trees that you're going to need, but you may be overfitting a bit. And the third parameter that you're going to have to set is this number of splits that you want to have, which is D. All right. So at this point, I want to go flip over to a Markdown document and just illustrate this method. So if you haven't watched my random forest lectures, so there were 2 videos on random forests, you should do so because I give a bit more detail about these data sets. I'm kind of just applying the same data sets applying GBM to the same data sets that I applied my random forests to. So let's go to the Washington, D.C. bike sharing data set. And so remember, the goal was to predict the number of rentals that you're going to have in a given day. So I just brought in the data. I made some of my variables factors. So day of the week, I recoded as a factor. Season of the year, I made a factor. And year, I made into a factor, likewise with the weather situation. How do I fit a gradient boosting model, gradient boosting machine model? I use GBM. Now, the syntax for this looks a lot like the syntax that we've had for all of our modeling commands. So we give it a formula, and we give it a data frame. As with random forests, if you make your dependent variable a factor, you're going to get classification trees. If it's a number, then if it's a numeric variable, then you're going to get regression trees, and it will assume Gaussian distributions, just like GLM did, or random forests. Now, the first thing I'm going to show you is an additional function that we're going to use that I guess we haven't quite seen anything like this yet. And it's gbm.performance, PERF. And so when you plot gbm.performance, you get to see how the objective function, so we want to minimize the sum of squared errors, so that's a squared error loss, as a function of the iterations. So how do my sums of squares decrease as I do more and more iterations? And so what you'll see is that I'm learning quite rapidly. So by about the 40th iteration or so, I've gotten much of my my reduction that I'm going to get. It goes down a bit further. The default stopping point for the number of trees is 100. And so when I see this, it looks like if I were to carry on a bit further, I could reduce my squared error loss a bit further. In the next example, I'm going to show us how we can get a test set or cross-validation to help us make this decision. So you can think about this is really that bias variance plot that we've been talking about. Remember, we have the complexity of the model. Here's your training set. Here's your test set. And our goal is to pick a value that minimizes the test set error. So in this case, we make our model more complicated in part by adding more stumps to the mix. So this, you can think of this as the number of trees or the number of stumps with which is what it is in this case. I believe the default is to give us stumps. So I'm not going to have a test set for now. We're going to push that off to the next example. Instead, I'd like to show you some of the other functions that are available with this. So if I do summary on this, I'm going to get a variable importance plot. So with random forest, I did var imp plot to get this. Here I get I get two things. So I get the plots, which I wish these things would be rotated so that I could see them all. You can see that because of the number of variables, we don't know what these labels are. So you're probably wondering, what are these other labels? Well, if you go down, the summary function also prints out the variables. So you can see temperature is the one that is the most important in this model. The next most important is year. And so this is entirely consistent with what we found with our random forest model. The way this is computed is similar. So we're keeping track of how much this variable explains in the dependent variable. And it's scaled in a certain way. So, as we found with random forest, temperature is you don't want to go biking when it's freezing out. You don't want to go biking when it's extremely hot out. But if it's somewhere in the middle, you're going to be happy. All right. So that's the variable importance. You can think of this as like var imp plot, and this is importance. All of that gets produced by the summary function of a GBM model. Well, another thing that we get built in are various partial dependence plots, just as we got with the partial plot function in the random forest package. So the difference here is that we're going to use the plot command. So when we plot a GBM object, you can specify some variable in quotes. For example, maybe I want to look at the temperature effect. And so what this is saying is when it's really cold out, you don't have a lot of bicycle rentals. As the temperature gets warmer, you have a lot more bicycle rentals until some point when the demand falls off, because if it's 100 and some degrees in Washington, D.C., you don't want to be biking. Well, there's still a fair number of rentals, but not as many if it's sort of in the 80s or 70s when it's very nice out. And well, we could go look at year. And so when we look at year, what you're going to see is what we saw before. There's a lot more rentals in the second year of the program than there was in the first year of the program, indicating the program was being adopted by more people. It takes a while to make your way up the adoption curve. If you have another categorical predictor like season, you can look at the effects. Here's a partial plot for that, and what it shows is we don't see a lot of rentals in winter. We see the most rentals in summer and also in fall, fewer in spring. I just showed a couple more variables. Weather situation, if it's clear, you have a lot of rentals. This is light rain or snow, so you don't get a lot of rentals when it's snowing. So nothing surprising there. Here's the humidity variable, and what we see is that if it's extremely humid, you see fewer rentals even after you've controlled for temperature. So we saw a lot of these things when we analyzed this data set with the generalized additive model, pretty similar effects, and also with the random forests. Let's go on, and I also talked about the saddle function. So remember, the saddle function is where you have, say, x1 times x2 over the interval -1 to +1. And I'm going to add a little bit of Gaussian noise to it. And so I pointed out that this is an extremely difficult function because it involves this interaction between two numerical variables. So an additive model can't handle this at all because there's an interaction. We saw last time that random forests actually did a remarkable job with this. This is not an easy function. Let's see how GBM does on it. So I'm going to modify my call just slightly. So let's regress y on everything else. So everything else would be x1 and x2. I'm going to add a few terms. Now I know I'm going to have to capture some interactions. So this is the D parameter. So remember I said D is the depth of your tree. And so I'm going to make the interaction depth 2 so that my trees are capable of modeling interactions. What would be an interesting exercise is for you to try setting this equal to 1. And what you should find is that the trees, the gradient boosting machine doesn't learn at all with with an interaction depth of 1. So it's really important that if you have interactions, this has to be greater than 1. I'm also going to give us quite a few trees. So let's go give ourselves 5,000 trees. We stopped at 100 in the previous example. And I'm going to be a little bit more aggressive in my learning. So we're going to make the learning rate about 2% rather than what we had before. Now, the other thing I'm going to be concerned with here is getting honest estimates of my prediction error. So the way I can handle this is by using k-fold cross-validation. And so GBM makes it extremely easy to do that. So I've set the number of folds to 5 here. So I'm going to do 5-fold cross-validation. Well, I fitted my model. This one actually took seconds to run on my fast PC because I have a data set with 10,000 points and doing these the cross-validation. So this was not an instantaneous fit. Now, when I do my GBM.performance plot, what you're going to see is that we get 2 lines now. So the green line is showing our test set error, so cross-validated error. The black line is showing my training error, and this is your classic bias variance plot. So maybe not quite as dramatic as this, but we're seeing the same thing here. So this green plot goes down basically at the same rate as the training error until we start passing about 1,000 trees. And then what happens is the green line actually keeps going down until we hit this point, around 2,000 trees. And then it's hard to tell, but it's actually going up. So it gets really flat around 1,000 trees. We're not making much progress beyond that. The green line actually says that we make a tiny bit of progress, but you might want to stop a little bit early because going from 1,000 to 2,000 trees gets you almost nothing in test set or cross-validated error, but increases the complexity of your model substantially. So you have twice the number of trees. You can see where as I keep increasing the number of trees, the training set error keeps reducing. So I haven't gone beyond this, but presumably we could push it even a bit lower. That's not necessarily going to help us on the test set error. I'll just point out, remember I added noise at the rate of sigma squared over 4. The variance was 1/16. So that'd be, I took a z variable divided by 4. So 1/16 is 0.0625. And so just eyeballing this graph, I think we're really close to what the true error rate is. So GBM has done an incredible job. So let's just go look at our variable importance plot. So I do that with summary, and what we see is it looks like x1 appears to be a little more important than x2 in this model, although both variables are pretty important. We get an error message saying there are 2 predictors, of which both of them had non-zero influence, and I would actually expect the importances to be equal here because that's the way I rigged the problem. We can go look at our numeric version of that plot and comes to the same conclusion. All right, well, let's go now look at our partial plots. We looked at these for the saddle function using the partial plot function with a random forest, and we said it was not telling us anything because it's nonsense. Why is it nonsense? Well, the effect of one x on y in the presence of an interaction means that effect depends on the value of the other x. And so we see the same thing when we look at these one-dimensional partial plots from GBM. So basically, this is a flat function. It's wiggling a lot, but when you look at the scale, it's wiggling a lot near zero. What would be nice is to expand the scale, which is what I did on the partial plot, to show that it's really pretty flat. Likewise, if we look at the partial plot for x2, it's also flat. Well, a nice thing about GBM is it actually will do partial plots that will allow you to visualize an interaction. So if you, instead of specifying, what I was passing to it here was the second index. So that means the second column. This was the first column. If I pass to it both columns as a vector, it's going to compute a partial plot using an image. So this is an image plot. And so we're plotting x2 versus x1. We're encoding the height of the function using color. So when this image plot is yellow, the plot is very large, around 1. And so what you'll see is that when both x1 and x2 are positive, remember this is x1 times x2, so these are positive numbers when both x1 and x2 are positive. We also see the yellow down here when both values are negative. Likewise, dark blue indicates very negative values, and so this would be, your legs would go here, and your body would kind of, this is where the function's going up. And so this partial plot has done a pretty good job of capturing this very complicated interaction function. Now, I'll just return to ALE plots. So with an ALE plot, that was something that we went over in the random forest lecture, that's another way to visualize the interactions, and ALE plots have advantages over the partial plots. So this is definitely something you want to get to know. The ALE plot requires you to define a prediction function, and in here I gave an extra argument to my predict function saying, don't use all 5,000 trees. My cross-validation said maybe 1,900 trees are good enough. So just use the first 1,900 trees when you make your predictions. So here's the ALE plot version of that interaction plot, and so you see the same phenomena. There's also contours indicated. So you see all these contours are going up. All the contours here are going up, whereas the contours, if you go in the other direction, are getting negative. And so the contour plot has done a good job of visualizing this as well. Well, let's go back to my course packet, and I want to wrap things up with an overview. So we've covered a whole lot of methods this week. We actually covered a lot of methods in this course, but this is going to give us an overview of when to do what. So basic trees, so what I mean by that are, single cart tree, have a number of advantages. They're extremely fast. They're extremely easy to explain. Go back and look at some of those videos and give some great examples of how you could explain one of these trees to someone who's not a data scientist and they would get it right away. So they're easy to explain, interpret, and implement. If you have to go implement a tree in SQL, it's not a big deal. Problem with these basic trees is that they're okay but not great predictors. So if they were great predictors, we never would have had to create random forests or boosted trees. So the reason they're not such great predictors is because they produce step functions, and so they don't approximate smooth functions very well. Another huge advantage of every method that I've talked about this week is that they're robust to outlying x values. We don't need to worry about finding transformations of our x's. So that was a big task that we had to deal with back with regression, logistic regression. So that's not a problem with us. All these methods are extremely good with missing values. I'll also say they're very good with categorical variables that take a lot of values. So I mentioned that back during the CART lecture. So if you have a variable like state of residence that takes 50 values, a tree method will just introduce splits where they're needed. Regression model is going to include 50 dummies, or 49 dummies, and burn up a lot of degrees of freedom and lead to overfitting. If you want to find interactions with state, the regression models are going to be even worse. All right. So a couple more things. Random forests and bag trees, boosted trees, are usually among the best in class. So especially for classification problems, these will be among your top predictors often. They require little user intervention, especially random forests. The only thing you need to worry about with random forests is how many trees are there in your forest. With boosted trees, you have a few more things to tune. You got to worry about your interaction depth, and you have to worry about the learning rate in addition to the number of trees. These methods are fairly robust to overfitting, so that's another big plus. Random forests and bag trees lend themselves to parallel computation. I'll just mention one other really big advantage of random forests. So remember what random forests do. They select a subset of predictors to search at each node. What that means is you've just reduced your computation by a lot. So let's say I had 100 predictors. If I'm only going to search through the square root of 100 or 10 predictors at each split, well, that means I only have to search 10 variables instead of 100 variables at each split. So you're going to find it goes a lot faster than bagged trees where you're searching all 100. And I also find it to be a bit faster than boosted trees. I just mentioned that there's been a lot of good work done on trying to help us understand the most important variables and how they affect Y. And so the variable importance measures do that, and the partial dependence plots allow us to understand these interpret the effects. But I did mention a couple important things about them. So variable importance measures are not immune to multicollinearity. If you have many highly correlated predictors in your model, as we saw with the bike share example, some of those predictors, they'll share the explanation and not come up as much. Whereas if you got rid of some of the highly correlated variables, then the ones that you left in there will get to enter into more splits and appear to be more important. So that's one just limitation to keep in mind when you do this. We saw that partial dependence plots can be misleading if you have interactions. Of course, there are partial dependence plots that show these interactions, so that's good, but just be aware of that. So I would treat them as exploratory, and I would compare them with different approaches. So when I approach a machine learning problem, I tend to try all the methods and hopefully come to the same conclusions with the different methods. If I come to different conclusions, so if I'm finding that my random forests and boosted trees are giving me much lower cross-validated errors than, say, a linear regression or a generalized additive model, what that signals to me is I probably have missed some interactions. There's some interactions out there that I don't really understand because random forests have found them for me, and I haven't coded for those in the logistic regression model. So I hope you've enjoyed this module on predictive methods. I've tried to give you a survey of all the different approaches and given you a lot of very powerful tools for your toolbox. There's more to learn though, so there's some methods that we haven't had a chance to cover in this class, like support vector machines or neural networks. I'll probably put some videos up on those if you're interested in studying those.